Hi everybody. Today we're going to be talking about how to name and write formulas for simple binary ionic compounds. This is the first lesson in Unit 2B on ionic bonding. Okay, so you might remember from the last unit of study that generally ionic bonding happens whenever you have a metal and a nonmetal. Due to a big difference in electronegativity, one atom, the metal, is typically going to give up electrons to the nonmetal so that the metal becomes positively charged and the nonmetal becomes negatively charged, and those two ions then can stick together. Now, probably the first skill that you need if you're going to be writing formulas for ionic compounds is to be able to predict the charge of ions. And you might remember you can kind of do this fairly easily by looking at the column that elements are in. Elements in this first column are all +1 charged elements. Elements in this second column tend to make +2. And then when you get over here in the boron aluminum family, you get +3, there's a plus or minus 4, and then it goes, I didn't quite leave myself enough room here, but -3, -2, and -1. Okay, -1 over the fluorine family in the periodic table. So if you kind of do this based on the column, you can see nitrogen's in the -3 family over here. So nitrogen would have a -3 charge. Cesium is over here in the +1 family, so it would have a +1 charge. Strontium is in the second family, the alkaline earth metals, and that whole family tends to take a +2 charge. Chlorine would be -1, and selenium would be -2. So if you need to go back and do a little additional practice for making sure that you can easily identify the charge of elements, then you may want to take a look at your reference periodic table. It has those charges on it for you on the green reference periodic table that I provide. Okay, so if you're going to predict the formula for ionic compounds, the biggest idea here is that the total charge of all of the atoms added together has to equal 0. Okay, so the total charge has to equal 0. And so if you start looking at, combining elements that are positive and negative together, probably the simplest case would be one where the first element has just like a +1 charge and the next element has a -1 charge. And if you combine those together, only one of each would be needed. And so the formula for lithium chloride would only have one lithium and one chlorine in it in a 1-to-1 ratio. The formula then would just be LiCl. Now, if your amount of positive charge isn't the same as your amount of negative charge, then you might have to have more of one atom or the other. In this case, sodium's a +1 and oxygen is a -2. And so, if you're going to try to figure out, okay, how do I, get this thing to be neutrally charged? Well, it would take another +1 sodium, because each sodium is a +1, to balance out with a single -2 oxygen, so that the total of +2 and -2 adds up to 0. And so the formula for sodium oxide would be Na2O. And notice we didn't write ones in these formulas. The ones are understood. So this just says, hey, I've got 2 sodiums for every 1 oxygen in the formula. All right, now if you're going to do this for something like aluminum sulfide, this can get a little bit more complicated. I'm going to come over here just for a second. Okay, so aluminum is a +3, and sulfur is a -2. And if you start looking, okay, how many of each of these is it going to take before the total positive charge and negative charge balances out, then you see right now I've got more positive than negative. And so I can add more negative by adding another sulfur that's -2. Okay, but each sulfur is -2. So I still don't have a balanced scenario. If I look here, I've got +3 and a total of -4 on my 2 sulfurs. And so, I've got more negative than positive. Maybe I need to add another aluminum. So now that's 2 aluminums that total to +6. It looks like it's going to take one more sulfur to get to a total of -6. So here's the first, the smallest amount of each one of these that I can get where the total positive charge and the total negative charge is balanced. And so, because it took 2 aluminums and 3 sulfurs to do that, the formula for aluminum sulfide would be Al2S3. Now here's a neat little trick that you can use to do this sometimes. If you kind of write the metal and the non-metal with their charges kind of like I have right here, then you can use something called the crisscross method. And basically, this little 2 comes down on the aluminum, you can see that there, and the 3 comes down on the sulfur, and you can see that there. That is kind of a shortcut method for getting a neutrally charged formula. Now, something that's important to keep in mind, though, is that that ratio needs to be reduced. And we'll show that down here in just a second. All right, so using this new method, if I were taking a look at something like calcium with a +2, phosphide with a -3, then if I were to crisscross those charges to get the number of each, it would take 3 calciums and 2 phosphoruses to get to a total. And you see 3 of these would total to 3 +2s is +6 and 2 -3s is -6. For magnesium fluoride, magnesium, if you find its charge, is +2, fluorine is -1. So this formula would be MgF2. It would take 2 fluorines that are each -1 to balance out with that +2 magnesium. Okay. Now, sometimes on the periodic table you can't see what the charge is for elements, and so if you see a Roman number, then the Roman number is going to be the charge of the very first element in that formula. If you look for iron on the periodic table, iron on the periodic table is like right about here, and there's no way to predict what the charge of iron is going to be. And part of the reason for that is that iron can take different charges in different scenarios. Many of the transition metals, the ones in the middle of the periodic table here, can do that. But this in particular name is telling us that the iron is a +3 charge here. So we know that the Fe iron is a +3 in this scenario, and the oxygen over here is predictably -2. And so if you used your crisscross method, you could say, okay, there's got to be 2 irons and 3 oxygens in the formula. Okay. The reason for this, again, is that the total charge has to add up to 0. Two +3s would be +6, and 3 -2s would be -6, so the 2 charges are balanced there. If you take a look at this one, the Roman number IV is the Roman number 4. And so titanium in this one is a +4 charge, and oxygen is a -2 charge. And so if you did your crisscross method, you would get Ti2O4. The 2 comes down on the titanium and the 4 comes down on the oxygen to say we've got 2 of these and 4 of these. Now, when you put those numbers down at the bottom, I want to really make sure that you understand that these are not charges anymore. These are literally how many of each do you have in the formula? What is the ratio of those 2 things? Now, there's a problem with this formula. Formulas need to be in the lowest ratio. So these, a 1-to-1 ratio can't be reduced. A 2-to-1 ratio cannot be reduced. 2-to-3 or 3-to-2 cannot be reduced. But a 2-to-4 ratio can be reduced. And here's what I mean by that. You can divide a number evenly into both of these subscripts. The number 2 divides evenly into 2 once, and the number 2 divides evenly into 4 twice. And so a better formula for this would be TiO2. And if you go back to kind of the basics of the total charge has to add up to 0, you can see, well, it's really only going to take 2 of these -2s to balance out 1 of these +4s. Okay, so that's a little bit about how to write the formula for ionic compounds. All right, so when you're naming binary compounds, we already learned how to name covalent compounds in the last unit. These things use prefixes, and covalent compounds were going to be compounds that had basically no metals in them. And so, if you want to find out if a compound is covalent, just ask yourself, does it have a metal? If the answer is no, then you're going to use the same rules that we used in the last unit, where if you had just like two nonmetals, you use those prefixes like mono, di, tri, tetra, penta, hepta, hex, octa, nona, deca, and you put an "ide" on the second element. For example, N2O4 would have been dinitrogen for the two N's and tetraoxide. Okay. Now, ionic compounds have a completely different set of rules. So let's take a look at a couple of examples. So metals can have fixed charges. When we say a charge is fixed, we're saying that a charge is predictable. And so, like I was saying back in the kind of the beginning of here, if your metal is in one of these columns that has a predictable charge, or there's three metals that are predictably charged here, zinc and cadmium and silver, I believe. Those three metals are predictably charged at +2, +2, and +1. Any of those, or any of the ones that are in the tall columns, would be metals that have predictable charges. And so if you have that kind of predictable charge, then naming a compound is super easy. So for example, we're only going to use an "ide" ending on those kinds, and so something like Li2 is just lithium oxide. Now, this is really important. Notice what's missing from this name that we have over here. There are no prefixes. There is nothing in the name lithium oxide to say anything about that 2. And the reason for that is that, well, if someone was looking at this name, lithium oxide, and they wanted to go back to the formula, lithium is a +1, oxygen is a -2, and so predictably they would have to say, oh, it takes 2 lithiums to balance the charge of 1 -2 oxygen, since each lithium is +1 and the oxygen's -2. Now, for metals, sometimes metals have an unpredictable charge. And so iron was an example for that in the last example over here. It was in the middle of the periodic table. You cannot tell what the charge is going to be simply from the position of that element in the periodic table. And so to name a compound like that, we've got to put some extra information in the name that we did not have here. And that extra information is going to be a Roman number. Now, hopefully you know your Roman numbers, but if not, you probably need to learn them up to about 6 or 7. So just if we kind of take a quick look, 1, 2, 3, 4, 5, 6, 7. Roman numbers are just I. Now, Roman number for 5 is a V. The Roman number for 4 is 1 before 5. And so they write this as an IV. The Roman number for 6 is 1 after 5, and so they write this as VI. The Roman number for 7 is 2 after 5, and so they write this as VII. So you may want to take a moment and just make sure that you kind of memorize what the Roman numbers look like and how to know what those numbers are. So the idea here in these compounds where you have a metal with an unpredictable charge is that the Roman number needs to be whatever the charge is on one of the metal atoms in the formula. Okay, so for instance here, if I've got this compound FeO, yes, I'm going to put the odd ending on the second element just like I did before, but the addition is that I need to figure out what the charge on this metal is. Now, the nonmetal's charge is going to be predictable. So you can say FeO, the O has a -2, and so then ask yourself, what does the charge on the iron have to be? And to balance it out, it's going to have to be a +2. So this Roman number 2 in the name, iron 2 oxide, is telling you that the Roman number is 2. Let's compare that to maybe Fe2O3. Now, each oxygen in this one is -2, and if you look at the total charge of all the oxygens, it's a -6. The total charge of both irons would have to be a +6, but 6 is not your Roman number. 6 would have to be divided by 2 to get the charge on each iron, And so each iron in this one would have to be +3. I have 2 +3s, so this one would be iron Roman number 3 oxide. Okay,